Thank you very much for coming. I introduce today's speaker. Before that, as you may know, that well, some of you may know that I have many offices in Taipei, especially open only at night time. And after AC stop here, I go to those offices almost every night. And one time, one of the offices, I was reading the draft paper with one of my colleagues, and a big number of people came in. So I was asked to move to the other table to share with the other customer in the office. And so that I moved to the table, and I was drinking liquid bread at that time, always. And then suddenly the owner of that office told me, both of you are Japanese. Satoki-san, this is Yuki-san. Yuki-san, this is Satoki-san. Please talk to each other. And then that's our first time meet. Then that day, after a lot of liquid bread, and noticed that, well, where he's working, Chongli, and Japanese in Chongli, there's only one solution. Oh, so you're working for the NCU? Yes. Which field? Physics. Okay, that's very close to me. Which field of physics? Cosmology. Oh, I'm working for the ASIAA, ASIAA. Then, oh, I know Keiichi Umetsu, and I know Teppei Okura, and I know Inoue-san. Oh, wait, what? And turned out that he graduated the same university as me, and shared some, like my former instrumental supervisor, Matsuo-san, when I was a PhD student, and he worked with him and referred our papers, and it turned out that we are very close, but we never met, except for the 1 year ago at the bar. Sorry, not at one of my office. And so this time, well, after I talked with him, I noticed his work is really interesting, so I decided to invite him. And today, first time I actually meet with him at the academic place. But today he's going to talk about the opening of the experimental approach for gravitational wave science in Taiwan. But before that, I will introduce officially academic positions. He graduated the Graduate University for the Advanced Studies in Japan. That's where I also graduated in 2016. Then he moved to Taiwan, Academic Institute of Physics in 2016, April. Then first postdoc, and 1 year later he got the distinguished postdoctoral fellow position in Academia IOP. Then 2018 he got the faculty position in National Central University. And at that time, well, in the PhD he was doing the cosmic microwave background experiment, polar bear, and when he moved here, he started the KAGRA in gravitational wave, and now he changed to the LIGO, and today he's going to talk about the activity of LIGO in Taiwan. So please welcome our speaker.
Thank you. So I'm very happy to discuss about our future science about the gravitational wave in ASIAA. So so I'm Yuki Inoue from National Central University. Today I would like to explain about the opening of experimental approach for gravitational wave in Taiwan. So in first step I would like to introduce myself. So my name is Yuki Inoue. So please call me Yuki. So I'm an assistant professor in National Central University. And as he said, my research history is very similar to astronomical field. And in first step, I joined the polar bear and polar bear 2 experiment. And I studied about their cosmic microwave background experiment. Sometimes I went to Chile or Takama and do something commissioning work for their observation. And after that, I decided to move KAGRA experiment and start the gravitational wave experiment in Japan. So just on time, so LIGO detect the gravitational wave. So this period is kind of phase transition error to the observation error. For the noise hunting error to the observation error. So at that time, so once we observe the something target, so calibration is one of the important works. So I decided to contribute to calibration work in KAGRA. And after that, just this year, so we decided to move a LIGO experiment. So LIGO is one of the largest gravitational wave detector in the US. And I joined this experiment and do the research. And also today, I would like to discuss about the future R&D in Taiwan. So, and if you have any opinion or idea, so it's I'm very happy to discuss about it. So anyway, so today I want to discuss about it. So this is our group, and we took this picture last week. So this is the gravitational wave experiment team of LIGO Taiwan. So I am a PI of LIGO Taiwan, and we organize these teams. And this team is from Academia Sinica and National Tsinghua University, and we are doing the analysis and experimental R&D in this group. So so as you can see, each institute is very close, so we can easy to communicate each other. So sometimes my students go to the NCU and do their coding work, and sometimes Academia Sinica fellow come to my laboratory and do the analysis discussion and some optical discussion, and we communicate every week. So from next year, Professor Chow in NTHU will retire. So after that, we plan to take over the coding technology. This is because this technology is essential technology for current LIGO experiment. So now we are doing such kind of activity as LIGO collaborators. Okay, so this is the outline of this talk. First, I would like to explain about the introduction, gravitational wave source, LIGO, and future R&D. And finally, I would like to do some discussion in the question section. Okay, maybe I heard almost all, a lot of audience is studying about the black hole. So maybe, you already know these things, but maybe I try to explain for faster. So in our experiment, we observed the gravitational wave. So gravitational wave is one of the most important prediction of general relativity. So just 6 years ago, LIGO succeeded to observe the gravitational wave signal, and after that they improved the system, and nowadays so we can observe the gravitational wave every 10 days. So by using this signal, we start the research about the general relativity and such kind of science now. So maybe to explain the gravitational wave, so we need to explain about the distortion of space. So maybe at that time we can use the an apple. So we put a 4 apple around the Earth. At that time, Earth have a mass. So Earth makes such kind of gravity potential. Of course, if we put the apple around the Earth, apple moves to the center of the Earth. So if we use the context of potential, so this apple roll on this slope, and finally apple moves to the minimum point of this potential. So, but even if we put a massive object on the space, we cannot make a gravitational wave. So we need to shape the massive object on the space. Then we can generate a gravitational wave. So this is a kind of analogy of electromagnetic wave. When we studying about the electromagnetic wave, so we need to shape the charged particle at that time, so this charged particle makes electromagnetic wave. So yeah, if we put shape something object, then we can generate the gravitational wave. However, yeah, even if we put the Earth, it doesn't vibrate automatically. But we can consider a similar system, which is binary star. If we consider the binary star, it makes a lot of it makes perturbation in the metric. Then we can observe this distortion of space with the detector. So yeah, so I said metric. So actually, gravitational wave is metric perturbation. So when we observe the gravitational wave, every time we need to measure this value. So by solving the Einstein equation, so we can get a wave equation. So it means that the gravitational wave propagate on the with speed of light, and also a gravitational wave have polarization. So one polarization is plus mode and another polarization is cross mode. So by assuming this mode, so we can observe the gravitational wave signal. So in next step, I would like to explain the gravitational wave source. Okay. So when we studying about the gravitational wave, we can categorize some gravitational wave source. One is binary systems, and second is supernova, such kind of burst-like event, and the pulsar, and also so pulsar generate a continuous wave and stochastic background. So so now before observation 3, so last observation, so they observed three targets, so which is black hole matter and neutron subordinate. And also in first event, they succeeded to catch the follow-up signal with electromagnetic wave. So recently, so this is a picture of compact binary fluorescence. So when we observe the gravitational wave signal, then we can observe the chart signal. So this is the observed gravitational wave form, and we analyze the changes of frequency and shapes by using the output signal. So this waveform is corresponding to the in-spiral, matter, and ring-down phase. Then we can know the gravitational wave information by analyzing this waveform. So recently, so LIGO LIGO project published the black hole neutron star matter event. So published on June 29 this year. So in this paper, so we observed the black hole and neutron star. So yeah, so now we observed these events at the same two events at the same time. So now we can put the check mark to the VHNS. So after the, I think after the observation 3, so we observed the next target, so which is supernova, pulsar, and stochastic. But I think sensitivity of current LIGO-KAGRA detector is not focused on the stochastic background. So I think it will be measured by maybe DESIGO or pulsar timing array. But yeah, so in LIGO, so we also trying to analyze the supernova and the pulsars event by using the previous data. So anyway, so this is a gravitational wave target. So this is a measured black hole in previous measurement. So y-axis is corresponding to the mass, and these are a variety of black hole signal. And by assuming current sensitivity, so we can observe the gravitational wave every 10 days. So but now we are upgrading the system. So we plan to start the next observation from next summer. So at that time, we are expected to observe the more events. So in this event, we have some interesting event. So one is neutron star. As you can see, we have really few events, and some event is so in first event, so we succeeded to catch the electromagnetic wave at the same time. But second event, so unfortunately, we cannot find some counterpart. So in observation 4, so we try to get more event and cross-check this phenomena. And also, mass gap region is kind of new science. So this is because if we increase the mass of neutron star, it will be changed to the black hole. But it depends on the state of equation, so that we have some uncertainty. So no one knows the threshold between the two regions. And also, we also have our new science about the intermediate black hole. So in observation 3, so we observed this event, and this typical mass is larger than 80, and finally it reached to the about 160. So, but this is only one event. So we hope we will accumulate such kind of important event in observation 4 and know the detailed information about these science. So this picture shows the multi-messenger astronomy by using the GW170817. So 2017, so LIGO and Virgo achieved to observe the binary neutron star event. At that time, after the observation, LIGO sent the information to the multi-messenger astronomical group. Then a lot of observatory catch the light curve after the observation. And this signal is gamma ray, and this event is from the optical IR telescope, and they successfully observed this event. So after they analyze this information, so they can understand the origin of heavy element, and we hope we get similar element in observation 4, and we confirm this phenomena for next observation. So as I said, when we observe the gravitational wave, so we analyze the waveform. At that time, we can pick up a lot of information. So first information is mass of two objects. Of course, we analyzing the binary systems. So important parameter is mass of two objects. So by analyzing data, we can know the charge mass and mass ratio. And also, we can define the merger time when two events merge at the same place. And the second point is detector geometry. So by analyzing the amplitude of gravitational waveform, at that time we can estimate the luminosity distance from the luminosity distance. Of course, this information is have some degeneracy with inclination angle. So by using the some gravitational wave detector, we need to solve this degeneracy. So and also we can know the elevation and azimuth angle of event, and we can also define the polarization angle of object. And finally, we can know the initial phase and initial frequency of this event. Then we can parameterize events with waveform. So so as I said, even if we observe the gravitational waveform with one detector, we need to solve the degeneracy of equation. This is because gravitational wave have a polarization. So in usual case, we detect the signal with sum of two signals. So at that time, we also have a degree of freedom of observation start position of this event. So and we also have a polarization angle. So if we separate this parameter, we have a 5 degree of freedom. So maybe you know, when you solve the simultaneous equation, we need to prepare the 5 independent equation if you have a 5 unknown factor. So we have to prepare the 5 independent equation. Okay, so if we observe the gravitational wave with one detector, maybe LIGO-Hanford observatory, at that time we can know the h of t information. Okay. However, if we increase the number of detectors, maybe Virgo, at that time we can measure the h of t from first detector, h of t of second detector, and we can also know the time interval between the two detectors. So we can get the 3 independent information. Okay, but we still need 2 parameters. If we increase the 3 detector, at that time we can get the 3 h of t, and time interval of first and second detector. Then we can get the 5 independent information. At that time we can solve the degeneracy of these parameters. But maybe you think about LIGO have a 2 detector, LIGO-Louisiana and LIGO-Livingston and LIGO-Hanford, and they also have a Virgo. So they already have 3 detectors. But unfortunately, LIGO designed the detector angle almost same. So this is because LIGO want to observe the first event. So at that time, if they change the angle, maybe one detector catch the gravitational wave, but they cannot catch the gravitational wave even in second detector. If they align their angle almost same, so they can publish the first detection paper with LIGO collaborator. So this is a kind of procedure. So they align almost same angle. So that if we want to solve the degeneracy, at that time we still need one detector. So from last year, KAGRA officially joined the LIGO-Virgo worldwide observation, worldwide collaborator. Then now they communicate each other, and KAGRA will also start observation from next year. So at that time, we can get 3 independent detectors. Then we can solve the degeneracy. So one of the interesting science in observation 4 is polarization. So we cannot solve the degeneracy of polarization with current detector, but if we add one detector, we can get the polarization information. So we can check some exotic model due to their relativity with this information. Okay, so do you have any question? If not, I move on the gravitational wave detector. Okay, so in next step, I explain about gravitational wave detector. So to discuss the gravitational wave detector, we need to discuss about the typical scale of a signal. Of course, when we develop something detector, we need to focus on the sensitivity. So now we assume the solar mass neutrons are binary. So this Schwarzschild radius is about 3 km. And now we assume the typical distance, which is 100 megaparsec. So nowadays we already know the gravitational wave amplitude, and I think this assumption is reasonable. So when we estimate the typical scale of h of t, so we can calculate the ratio of 2 values. So if we assume this value, so typical size of h is 10 to the minus 21st. So I'm from Japan, and here is Taipei. So if we measure the length between the Japan and Taipei, so this length is about 2,000 kilometers. So if we now, so of course h is metric, so no unit. So to know the typical scale, we need to multiply something length. So now we use this length as a reference. Okay, so if we assume a 2,000 kilometer, then we can get 10 to the minus 15 meter. This length is 1 femtometer. 1 femtometer is almost same as proton radius. So it means that we need to observe a very tiny change with the detector. So this is a gravitational wave observation. So to explain the principle of gravitational wave detector, so we would like to use the test masses. So it's very similar to electromagnetic wave. So maybe you remember when you learned electromagnetic wave, electromagnetic science in the school. Every time we observe the motion of charges, and if we apply something effect, at that time we monitor the motion of charges. In the case of gravitational wave, we can use the masses. We put the mass on the space and we monitor the position of masses. Okay. Of course, so this is animation. Typical change is very tiny like this. But in this case, so I would like to extend the ratio of aspect ratio of this animation. But anyway, yeah. So this is a gravitational wave form, and the gravitational wave is tensor perturbation. So when we separate its component, so we can get a plus mode and a cross mode. So yeah. So if we can observe the motion of these particles, then we can detect the gravitational wave. What do you think about how? So in this case, we focus on the two masses. Okay. So so in first step, we replace the two masses to the mirror. Okay. At that time, of course, we put this mirror here, and this is a test mass. If we increase the mass, so we can keep staying this object on the space. So we put a heavy mass to here. But when gravitational is allowed here, so this mass moves like this. Okay. Then we can observe the motion of this mirror. But we need to measure these changes. At that time, we can use the interferometer, Michelson type interferometer. First, we inject a laser from here, and we separate the two waves with beam splitter. And one beam goes to this direction, and other beam goes to this direction. In normal state, we don't catch the gravitational wave. At that time, we don't have any distortion. Okay, so at that time we keep this mirror position with feedback control. Then we can cancel this gravitational waveform. This is because this is laser, and if we cancel this interferometric signal, then we can get dark signal around here. But when gravitational wave arrive here, so this length will be changed. Then we can see the bright and dark signal. So this signal is corresponding to the chirp signal. So this is a first detection event of LIGO and Virgo, and yeah, they observed a gravitational waveform like this. So in this case, of course, so in principle we can observe the gravitational wave, but we don't have enough range with this method. This is because this wavelength is 1 micrometer. So even if we assume 1 micrometer, we cannot measure the tiny change. So we need to effectively extend the arm length. At that time, we can use the cavity technology. So if we put a cavity in the arm, then we can effectively extend the arm length. So we can observe this gravitational wave with enough sensitivity. Okay, so this is the overview of LIGO. So LIGO is second generation gravitational wave detector, and they have two detector systems in Hanford and Livingstone. And the arm length of LIGO is 4 kilometers. So they put the same design and detector at Hanford and Livingstone. Okay, in previous study, so LIGO achieved to observe out of event, and also they published some papers. So in this talk, I didn't focus on each topics, but yeah, so this is a picture from a previous publication. So this is the sensitivity of LIGO and Virgo. So purple line is from Virgo, and red and blue line is from LIGO harmful like Livingston. So yeah, so now they mark this sensitivity to observe the gravitational wave. By using the assumption of binary Newton star, so we estimate typical scale is 10 to the 21st. As you can see, so we can observe these signals with enough sensitivity. Okay. So this is a interferometer system. So as you can see, so LIGO's interferometer is really complicated. We combine a lot of cavity to observe the gravitational wave signal. So yeah, first they put the input monoclinic. So this one is called kind of Gaussian beam filter. We can only pick up the pure Gaussian beam. And this is a cavity, and this is a power recycling mirror. Of course, this is my personal setup. If we make an interferometer, so conduct signal go through this way, and this signal is also go to this way. So but we need to reduce this power in this cavity. This is because if we can increase the laser power, then we can extend the effective arm length more. So we put the power recycling cavity. Then we can kick back this signal to this cavity. And of course, cavity has some resonant frequency. And sometimes we want to tune the gravitational wave signal. At that time, we need to use this cavity. So yeah, by controlling the operation of this cavity, then we can tune the sensitive region. So yeah, so this technology is very important. This is because sometimes we have some unexpected noise. But if we cannot tune the sensitivity, maybe sensitive region is around here, but some noise covered at this region. But if we use the detuning technology, we can move the sensitive region to this frequency, and we can optimize the sensitivity with by using the situation of commissioning. So and maybe later, but I will explain the other application by using this technology with future plan. Anyway, so this is the interferometer overview. Okay, so this is the result of first to third observation. So x-axis is time and observation of time, and y-axis is corresponding to the measured events. In observation and observation 2, LIGO harmful Livingston operate the detector, but after at the end of observation 2, Virgo join to the observation. Then, as you can see, they increase the number of events dramatically, and now they keep the same ratio like this. So this is a typical sensitivity of each telescope. So now it's here. So of course, due to the COVID-19 situation, so LIGO have some delay. So in current plan, they plan to start observation around next summer, but they didn't decide yet. So, but in any case, they plan to increase sensitivity like this. We will also improve the sensitivity like this. So we are preparing the observation for in next year. And also in observation 5, LIGO India preparing the detector. At that time, they also joined the observation, and we observed the gravitational wave event with four detectors. If we separate the Livingston harmful, so we use the 5 detector. Okay. So after the 05, so they plan to upgrade LIGO Voyager LIGO-Voyager is kind of is cryogenic LIGO. So they plan to import the cryogenic technology from KAGRA, and they will improve the sensitivity at a low frequency. So this is a roadmap of LIGO scientific collaboration, and they will start the LIGO-Voyager study around this season. Okay, so and this is our contributions. So in previous study, we joined KAGRA. At that time, I organized the KAGRA calibration group as a chief. So in LIGO, I also continued a calibration study about the gravitational wave signal. So main purpose of calibration group is calibration of interferometer and the reconstruction of H of T. So even if we catch the something signal, so this is an electrical signal, we have to calculate the H of T from the data. So yeah, we developed the reconstruction pipeline of the signal, and we provide H of T to the all worldwide collaborator. Of course, when we do the calibration, so we can estimate the calibration uncertainty and the systematic error. So we also need to assign the systematic error of H of T. So yeah, we strongly contribute this part. So I think in observation 4, we will provide H of T data to the worldwide collaborator at that time. So I think yeah, this H of T and its uncertainty is part of Taiwan contribution. So yeah, we are studying about a very important part in LIGO group. And next is future study. So now we are strongly collaborate with NCU, so they have a coating lab. And in my previous research in cosmic microwave background, I studied about the coating. So I have some experience about the coating science. So yeah, we decide to accept the activity of his lab. So by using our cryogenic technology, so we plan to develop the coating characterization system under the cryogenic temperature. Of course, LIGO have a good characterization system already, but they only focus on the room temperature. This is because in previous studies, they focus on the room temperature of this. But in near future, they need to characterize the optical and mechanical performance with cryogenic system. So so yeah, we decided to develop this system. So now we are developing the prototype system in Academia Sinica. So yeah, we are also contributing this part. So, and also this is a future plan. So now LIGO have some test facility. Of course, when we want to install a new technology to LIGO, we need to do the test in somewhere. But so in US, they have a Caltech 40-meter telescope. In Europe, so they have a GEO and the Glasgow 10-meter telescope. But we don't have any test facility in Asia. So recently, I and Professor Henry Wong in Academia Sinica submitted a proposal to build the new test facility for gravitational wave science. And yeah, so so if we can have a test facility in Asia, so we can export our technology to the LIGO detection system. So this is a picture of LIGO test facility in ASIAA. And so we plan to build the interferometer system like this. And we also put the cryogenic system in this test facility and do the interferometer trigger experiment. So we in this on this Monday this week, so this proposal was accepted in ASIAA, and from next spring, so we will develop this test facility at the underground floor of Academia Sinica. So this space was used for the accelerator experiment in previous. but they bring this system to NCU now. So we plan to build the gravitational wave test facility in underground floor. So, and we also start the small R&D for this system. But anyway, I will explain the detail in later part. And this is a lab arrangement, and we discuss the possible environment for the system, and we measure something parameter to decide this part, and finally, yeah, we decide to fix this design. So okay, so this is a LIGO's activity in Taiwan. So in next step, I would like to explain the future plan in Taiwan. So maybe you know, in 2035, so gravitational wave community will develop the LISA, so which is future gravitational wave telescope. And of course, 2020, so we start gravitational wave observation with ground-based experiment. We have 15 years. So and also now is a COVID-19 period, so we can consider how to use this 15 years. So and of course, one possibility is we contribute the LIGO, and after the COVID-19 situation, we will visit to the LIGO. So this is one solution. But recently, we considered a new possibility. So this is a Taiwanese gravitational wave detector. But maybe you think about, so if we develop the Taiwanese gravitational wave detector, maybe we need to make a 4-kilometer tunnel. Yeah, this is because LIGO have a big detector. So, but I will explain why this is reasonable in this talk. Okay, so name is Kronos. So Kronos is cryogenic sub-Hertz cross-torsion detector with quantum non-denomination speedometer. So in this name, so we have 3 important technology: cryogenic, and second is torsion bar, and third is quantum non-denomination speedometer. So yeah, so by combining 3 technologies, so we can reduce the detector size to be 10 meter times 10 meter. So of course, we need to give up the current gravitational wave ranges, but by using this system, we can focus on the low frequency ranges. So I will explain the principle of this experiment. And as you can see, so this size is same as test facility of LIGO. So we and also this technology can be exported to the LIGO. So I plan to build this telescope as a LIGO test facility, and if we demonstrate something new technique, so we plan to export this idea to the LIGO, and yeah, so we plan to use this telescope. So even if we make a test facility, it also has science. Yeah, so this is a system. Okay, so this is a Kronos overview. So mission is a search for intermediate black hole on sub-Hertz range. So in current gravitational wave system, we can observe the 10 Hertz, 100 Hertz, 1000 Hertz. But in this detector, we focus on the sub-Hertz region. And method is interferometrical speedometer. So this measurement method is different from LIGO. And the full success is fast detection of intermediate black hole matter on 10 to the 4 region. Of course, we need to consider the ratio of it. So, but we can search this region potentially. And the unique point is 10 times 10 meter observatory. But to achieve this observatory, we need to get the 3 important technologies: cryogenic, speedometer, and torsion bar. Okay. So, and the location is underground site in Taiwan. This is because when we observe the low frequency region, so vibration from the ground is one of the serious problems. So we need to find the underground site in Taiwan. And R&D is ongoing. So now we are doing the R&D for key technologies, and we confirm the principle of this method. And in phase 2, we start integration test in academia center. And finally, we will bring the system to the underground site. And our target observation year is 2027. So yeah, 2027 is half of this year. So even if we have something there, we still have a lot of observation time. And this region is similar to LISA and such kind of experiment. So of course, sensitivity of LISA is better than this experiment, but we can touch this science region with this detector. So yeah, you know, yeah, LIGO and LIGO observe the black holes around the 10 mass solar mass region. And of course, the fact is that a supermass black hole exists in the universe. So it means that we have some intermediate space. But we don't know the story of intermediate black hole. So if we can observe this signal with detector, maybe we can model a scenario to generate these black holes. So this is a design of Chronos system. So in Chronos system, we put the second floor suspension, and we suspend the system with wire. And we put this system in first floor and put the entrance in server room. So maybe you know Taiwan have a lot of old tunnel. And last week, I and my postdoc, Daiki, went to the Hoton and entered the mine. And at that time, so yeah, so manager of Hoton said, so Taiwan have a lot of potentially a lot of tunnel. So to start the experiment, we need to know the kind of property of this site. But by using the old mine, so we can know the vibration level and so on before the experiment. So we plan to use the old mine for this experiment. And this design is based on the KAGRA. Okay, so this is N-test design. And we will use the sapphire torsion bar like this. And the temperature is 4 Kelvin, and total weight is 32 kilogram. And total moment of inertia is 2 kilogram meter square. So we put the torsion bar here. But maybe you think, why do we need a torsion bar? So this is because yeah, if we put the torsion bar on the space, so this torsion bar moves like this. So that one is distortion of gravitational wave. And if we put it on the space, then we can observe the motion of torsion bar. So to explain these things, we can use the example of previous information. So as I said, when we consider the gravitational wave detector, we can use a test mass on the space. And this is a LIGO-Virgo-KAGRA. And we can observe the motion of the test mass. In the case of previous experiment, so we can use the motion of test mass like this. But in the case of Chronos, we connect this test mass with torsion bar. So if we connect this torsion bar, at that time this test mass moves to this direction, and this test mass moves to this direction. Then we can observe the motion of torsion bar. If we can observe this motion, then we can catch the gravitational waveform. So in previous study, Toba, which is University of Tokyo, tried to develop a similar system. But according to this paper, so they require 10-meter sapphire. It's impossible to make it with current technology. But in this idea, we add another technique. Then we can reduce the size of the detector. Anyway, so and second is resonance frequency. when we observe the gravitational wave, so observation region is limited by the resonant frequency. In the case of LIGO-Virgo-KAGRA, they use a pendulum. So maybe you know a resonant frequency of pendulum is written by this equation. And if we put the typical length, so this value is 10 to the 0.1 Kelvin. So this is the reason why LIGO observed a signal above high frequency. But in the case of torsion bar, we don't use the pendulum motion. We use the rotation. So if we estimate the rotation of this signal, we can reduce the resonant frequency. It means that if we use the rotation, so we can extend the observation region to be lower frequency. So this is a principle. Of course, to observe the gravitational wave, we need to attenuate the vibration system, vibration from the ground. So at that time, we need to develop a seismic isolator. So this value is from the LIGO seismic isolator. So we plan to develop a similar one in Academia Sinica. So this is one of the demonstration of the cryogenic vibration isolation system. LIGO developed this isolator, but they didn't try the cryogenic operation. So if we succeed to demonstrate this isolator with cryogenic technology, so this is new technology, and we can export this technology to LIGO.
So you've got two bars hanging on two strings. Like
Yeah,
the two different strings. Like this 1 millimeter sapphire.
Mm-hmm.
You've got two strings for the.
Yeah. In the other case, we use the 3 strings.
3 strings.
Yeah, and we suspend this wire with 3 strings. So at that time, we can modify this equation, and this typical length is depend on the R from the center, and we can also get the similar resonant frequency.
But each bar is independently.
Yeah, independent.
So you've got 6 strings.
Yes, six strings.
So 3 strings per bar.
Yeah.
And then you got
6
holes
per
in like the bar has a hole, so
Yeah.
to suspend the lower bar.
Yeah, actually like this. So we suspend these testaments with a lot of wire. So in this case, we put the so this is a projection from here, but this number is 6. 1, 2, 3, 4, 5, 6. And yeah, and we suspended these masses with this design.
When by making this thing higher, you get to lower your frequency.
Yes. So in my calculation, so if we put this wire maybe 10 meter, so it means that if we make a second floor on the yeah. So of course we will optimize this number in the future, but I think if you have a 10 meter or something, so it's enough.
And the wire is cryogenic too.
No, cryogenic stage is only 3 stages. Above this stage, we don't use the cryogenic technology, so we use the room temperature.
So the bars are cold,
Yes.
but the strings are at room temperature.
Yes, exactly. And also, my student tried to estimate the resonant frequency with, so this is the 3 wire cases, and he analytically solved the equation. And I don't explain the detail, but they simulate solve this equation of motion. And finally, they estimate the typical frequency like this. And so this is a body diagram of this signal. And we are also trying to make a model of this suspension. And so this is the first idea, okay? And the second idea is speedometer. So even if we use the torsion bar, so we cannot achieve the 10 meter times 10 meter system. But we need to use the speedometer. So in this idea, so in any case, we need to monitor the position of this tester mass. At that time, we separate the laser into this direction and this direction, okay? And at that time, of course, time of this point is the same. And after that, this laser moves here. If it rotates here, so we can measure the changes of time interval between the here and here. If this bar moves here, so this timing is earlier than this timing. So we can observe the changes of unrelated. So we separate the two directions, and finally we merge at the same place. Then we can calculate the equation like this. Changes of phase is depend on the time of theta 1 and tau is time interval from here to here. And yeah, we can get these phase changes. On the other hand, this equation, so in this equation, so yeah, this laser hit at this surface first. So we can get this equation plus this equation. So this is an interferometer. We can calculate the differences of two signals. Then we can calculate the difference of two signals. So at that time, tau is same. This is because we share the same optics. So if we assume the constant tau, we can describe this equation. At that time, tau is constant, so output is corresponding to the W. So this is the angular velocity. It's a very important point. Originally, this idea is published from Glasgow team, and they are doing the R&D to apply future LIGO, and this is a Glasgow setup. And but we applied this idea to the torsion bar. So advantage of this idea is velocity. So when we write the harmonic oscillator, at that time we can calculate MA equals this equation. And if we need to measure this displacement, so we need to multiply dt second times, then we can get omega squared. But if value is corresponding to the omega, so it means that this value is corresponding proportional to 1 over omega. So we can reduce this field to be here. So by using this technology, we can improve the sensitivity at a low frequency. So of course, it's very similar to LIGO. So we need to put the mirror here, and we need to make a limit cavity, and we extend the size of the triangle. So yeah, we can increase the sensitivity. So this is the second technology. So even if we use this technology, so yeah, sometimes this noise limit the sensitivity. But if we employ this technology, we can solve the noise limit from this line to be here. Then we can improve the low frequency sensitivity. And final one is cryogenic technology. So of course, when we observe this signal, so Brownian motion at the surface is a serious problem. So we need to reduce the temperature of this wire. Then we can reduce the Brownian motion on the surface. Okay. So yeah, to reduce the cryogenic noise, so we hit this system with 4 Kelvin, and we put the 50 Kelvin stages to here. Then we can attenuate the cryogenic noise. So this is a calculated sensitivity, and the green line is from the suspension. So if we use the second floor suspension system, we can achieve this sensitivity. And the blue one is quantum noise based on the speedometer. And the red one is bar thermal noise. This one is a question to the temperature. If we increase the temperature, it moves here. And this one is from the vacuum requirement. So anyway, so we can write this sensitivity curve. Okay, so if we overplot the typical event, so green one is 50,000 mass solar mass, and blue one is 5,000 solar mass black hole. If we assume 100 megaparsec, so yeah, we can observe the 5,000 or something event with this by assuming this calculation. And also, yeah, if we, of course, in this calculation, we assume 100 megaparsec. If we assume the 1,000 solar masses event, and by changing the typical length, then we can overplot these lines. So these lines are from the Voyager. So Taiwan also strongly contributed the Voyager study. So if we observe the maybe 25 megaparsec, if we observe this event with 25 megaparsec, so we can observe something similar like this. And even if we observe this tiny event, we can follow up with LIGO-Voyager. So yeah, so after the announcement of LIGO-Voyager, we can try the reanalysis of the signal. Then maybe we can reach something science in this region. Anyway, so this is a sensitivity, expected sensitivity based on the typical signal. And we also have some variety of science, but today I just focus on these topics. And maybe time is
Almost.
okay. Okay, so yeah, maybe if we use the detuning technology, so what I said before, maybe if we can observe this signal earlier than Virgo, we can send the information to the LIGO and Virgo, and they detune this frequency. At that time, we can focus on this merger timing. Then we can try a test of GR if we can observe it earlier than LIGO and Virgo. Anyway, yeah, so this is expected science. And these are Chronos phase, and now is phase 1. And phase 2 observatory phase is already approved. And now yeah, we're considering where should we do in this experiment. And finally, yeah, I will briefly explain the current R&D. So now in NCU, so we make an interferometer system like this. And we can see there is an interferometer signal like this, and students try to use the interferometer for their experiment. So in near future, we will test the SANIAC interferometer. So this is small speedometer in NCU. So this is our current plan. And after we demonstrate this technology, we bring this optical system to the academia center. And also, this is a key point: digital control system. When we do the digital feedback control, we need to provide an online filter, and we need to make a feedback control with computer. And we also developed a Linux-based I/O system. And by using these systems, we can control the signal, and sometimes we can inject the signal and measure the transfer function and so on. And now we have this system in Academia Sinica and NCU. And yeah, this is the input optics. My student tried to develop the input optical system, and he already succeeded to load the interferometer like this. And yeah, we can observe a small noise if we say something, or if someone walks in the room, so we can see the signal. So, but yeah, anyway, the student trying to make her input optics. And this is the most important part, so vibration isolation system. Actually, half years ago, so we didn't achieve to make this system. But recently, my new postdoc joined our group, and after that, he started this study, and he spent only 4 months. But within 4 months, he developed this system and started characterization. And this is a control system like this. And actually, he had experience to develop a telescope in Chile. So he used this experience in astronomy to the system, and he characterizing this system now. So next is crowding system. So we also developed the active damping crowding system. Maybe you know when we use the crowding system in the telescope, sometimes this vibration propagates to the signal. And this is common problem in many experiments. So in this case, gravitational waves also have the same problem. So we developed active damping vibration isolation system and cancel the vibration at the cold stage of a system. And just 3 weeks ago, so we start the cryogenic operation test in Academia Sinica, and we start the cryogenic test in Academia Sinica. And this is a measurement in KK, and we also have a collaboration with KK, and they also measure the motion of head by using the laser displacement sensor. And typically, it have a 10 micrometer vibration. So we need to attenuate this vibration with actuator. And we plan to put actuator and sensor, and we make such kind of feedback loop. Then we can cancel the vibration motion on the stages. So recently, we have we collaborate with Polar Bear team. So they plan to develop the Simons Observatory in Chile, and also Shinji exposed future experiment. And Professor Masaya Hasegawa is in KK, and he have a cryogenic technology and experience to construct large instruments. And we have our advantage of feedback control system. So so we have a big collaboration between the two groups, and we developed this system now. Okay, so this is a summary. So we are studying the gravitational wave science as LIGO scientific collaboration. And the gravitational wave community will start the observation from next summer. And we expect to observe the gravitational wave signal every 10 days. And proposal of construction of GW test facility was approved in ASIAA. And we will test the future technologies and develop the prototype system of Kronos in AS. And the gravitational wave test facility will start from next October, and we are trying the demonstration R&D in NCU now. And if you are interested in the collaboration or future development, so we are very welcome. So we have a good, I think we have a good synergy for both institutes for future R&D. That's all. Thank you.
Very interesting, very interesting. So questions, comments?
Thank you. Just to see if I follow the basic concept of strain. First of all, for LIGO, I would have thought, I mean, you took Taiwan to Japan, but in practice, it's the length of the total, I guess, if you say that the light goes around some number of times, I mean, I don't think it actually matters where we are. In your case, your bar is only 10 meters in length, so you're measuring a displacement of a positional displacement of the bar. At 10 to the minus 18, okay, now you multiply this by 10 meters, that's the displacement you're looking for.
Yeah.
And 10 to the minus 18 of 10 meters is 10 to the minus 17 meters.
Yeah.
So you need to measure the position of your bar to 100 times better than LIGO does.
So I think, unfortunately, gravitational waveform have a cube. So we don't, even if we don't need to achieve the LIGO sensitivity around 10 to the 20 something. So so we can observe the gravitational wave signal at the low frequency region. So I think even if it is 10 to the minus 70 or something, we can catch some event. Yeah. So we don't need to achieve the 10 to. Of course, if we can achieve this sensitivity, it is better. But
I guess I'm just missing that. I mean, this is a strain, but LIGO's length is much longer.
Yeah.
So to get the same strain, or even to get 100 times worse strain than LIGO, you still have to make a much more accurate measurement. So are you saying you're actually measuring a position of your mirror more accurately than LIGO? Because you're using velocities instead of displacement? I mean, is that part of the story? It just seems to me that if you're how many femtometers you have to measure your position to, I think it's a smaller number than LIGO is measuring.
Okay, so it depends on the finesse of this cavity. So in our case, our finesse is much larger than LIGO. So this is because effective length is almost same as LIGO. When we calculate the vacuum sensitivity, so this sensitivity is almost same. It means that effective length is similar to LIGO.
So the displacement you measure is also a femtometer,
Yeah.
roughly.
Yeah. So, but if we make a high cavity system with large system, it's difficult. But this one is very small system. So, so I think technologically easier than LIGO. So this is the advantage with a small system. Yeah.
Ms. Kim?
Yeah, a few questions. So first, when you say quantum non-demolition speed meter, so what do you mean by quantum non-demolition?
Yeah. So when we observe the gravitational wave, so sensitivity is kind of trade-off. So so one is from the quantum noise is trade-off. One is from the shock noise, and another is from the radiation pressure noise. And of course, if we increase the laser power, radiation pressure noise increase, but shock noise decrease. But in this case, so we can solve this limit by using the speedometer technique. So so this line is quantum limit. So if we can measure this quantum limit, so it also have a science, and so this is the meaning of quantum demolition system. Yeah.
So the second one is that when you talk about sub-Hertz source, I mean, other than intermediate mass black hole, what other possibilities are there?
So other possibilities.
Say neutron star or even.
Unfortunately, this detector is not sensitive to neutron star binary, so we can only observe the binary neutron star. But maybe we can also analyze the continuous wave signal and such kind of other signal. But neutron star, if we write the neutron star typical sensitivity, so it runs here, so we cannot observe this event.
Okay. So sorry, the last one. So ASIOP, as you know, that is very close to a road next to it.
Yeah.
So it's very noisy a place. So are you sure that you want to put your interferometer there?
Yeah, it's very good point. So actually, so we measure the V1 floor vibration at the noon and noon and night. So of course we can observe the 10 times differences between the noon and night. It means that it is from the ground motion. So to do the, of course we cannot achieve the final sensitivity in academia sinica, but if dynamic range change the 10 times, so it's really difficult to keep the feedback control. So to attenuate these things, so we developed this vibration attenuation system. This is kind of spring of car, and we put a big spring here like this, and this dynamic range is much larger than this range, and we cancel this effect here. So we will put these instruments to here, then we can attenuate this effect from the load.
Just a brief comment about another origin of intermediate mass black holes. They may be also formed by from Hawksley zero metallicity stars as primordial.
I think if we can measure a lot of events and count some probability, maybe we can study about. But unfortunately, it is a weak point, so we don't have astronomical collaborator in this experiment. So if you have any ideas, please recommend. I would like to know the science possibility for the astronomical.
In this simulation, mass distribution peaks at much lower masses, around 100 or 300 solar masses, but there may be a possibility about 1,000.
Mhm. Yeah, so yeah, it's very interesting. So yeah.
So it's worth testing.
Okay, thank you.
Thank you.
Last question, if you have. If not, if you want to join dinner or beer, just let me know tonight. I don't know what time, but he will go to the lab tour after this to check out our cryogenic technology in IAA and see what it looks like. And so, okay, so thank you very much for this talk.